Okay, what I want to begin to discuss now is the inverse Laplace transform, and before I do that I want to talk a little bit about the use of Laplace transforms to solve differential equations, because it leads nicely into the material on the inverse transform. Just to an easy, let's then do, let's say this is cosine of 2t. And we're going to let me put v here. We're going to let dv dt at t equals 0 equal 1, and v at 0 equals 0. So what we're going to do is we're going to take the transform of this entire equation, both sides. And so what we get out of that is, if you recall, dv dt goes to s v of s minus v at 0. And sorry, that's little v. And second derivative of v with respect to t squared goes to s squared v of s, and then minus s v of 0, and then minus v prime of 0. So what we're going to do is we're going to take these and make substitutions for our derivatives. So for that dv dt squared, we're going to substitute s v of s, and then, s squared v of s. And we have minus s. Now v of 0 was given as 0. And then we have minus v prime of 0, which is v prime of 0, 1. So we have minus 1. And then we have 2 times dv dt. So that'll be 2 times s v of s, and then once again minus v of 0, which is 0, so we won't put that explicitly this time. And then we have just v of t. Well, that's going to transform to v of s, and then that's equal to the cosine of 2t, which transforms into s over s squared plus 2 squared. So playing around with that a little bit, let's collect like terms on the left-hand side. So I have v of s times s squared plus 2s plus 3. And then we'll move this minus 1 over to the right-hand side, so that's equal to s over s squared plus 4 plus 1. Okay, and then to get v of s, we just divide both sides by polynomial multiplying v of s. So we'll have s over s squared plus 4 times s squared plus 2s plus 3 plus 1 over s squared plus 2s plus 3. So this is our Laplace transform of that differential equation. And you can see the nice thing is, first of all, if we go back and we look at our original equation, you see that it's inhomogeneous. So you have this inhomogeneous term on the right-hand side. It's also second order, and it's got some initial conditions. So this is an example of a problem that would be very difficult to solve if we were going to solve the differential equation. Okay, not very difficult, but kind of a pain. So what we're going to do is we're going to transform that whole thing, and we're going to get a Laplace expression. But now we have this expression of s, and really what we want is we want the solution. So the question is how to get v of t. And the answer is that you take the inverse transform. So we're going to take L minus 1 of V of S. Now we're not going to do this right now because I want to do a discussion of how to take an inverse transform, but I just wanted to point out we're going to be looking at some problems and some forms and talking about some sort of more theoretical stuff, and I wanted to point out that those equations that we're going to look at, this is the kind of where they come from. Now if you want to know what we're modeling here, this second order differential equation would actually model the voltage across the load of an RLC circuit that is excited with a source that is sinusoidal. So you would get an equation of this form to model that. So this is actually a circuit, a differential equation that could very well represent a voltage in an RLC circuit that includes sinusoidal source. And also note that this could be anything. It wouldn't have to be sinusoidal. It could be a step function. It could be an exponential. And I guess technically I should have put U of t here to indicate that this whole thing turns on at t equals 0. Okay, so anyway, that's how you're going to get some of the forms that we're going to discuss when we discuss the inverse transform, and that is what they physically represent.